Assalamualaikum and very good afternoon to all of you. So we continue with the AC circuit analysis, okay, which is I think a new topic where in the previous we are only concentrating on the DC circuit, okay. But before we go for the AC circuit, so we need to have some fundamentals to maybe to refresh back. I think you have been thought about this sinusoidal waveform and so on, okay, complex numbers. But I think it's good also if you can refresh, okay, the basic fundamental before we proceed using these complex numbers and sinusoidal waveform in the analysis. Okay, so overview. So this is the overview, meaning that as you stated earlier, so we will deal with the complex numbers, and also we will introduce you about what we call the phasor domains and the resistor, the relationship of the voltage and the current that flow into the resistor, the capacitor, and inductors. Okay, because we have two new element here that, okay, capacitor and inductor, where this actually is actually we consider as energy storage. Okay, it can store the energy, so meaning that the voltage and current relationship inside the circuit is no longer linear. Okay, and then after that we will introduce you what is the impedance, Z. The unit is still ohms. And then we will also introduce you about the admittance, which is Y. Y is actually the only actually the inverse of the impedance, and the unit is also MHO, mho, or sometimes it's also called a unit Siemens. So just a brief introductions about the circuits analysis. So what we have already discussed is actually on the DC circuits, where the source that involved in the analysis is a DC source, where the DC source meaning that it's actually a constant. Okay, so the voltage value is actually a constant values, and it is not time dependent. And then now we will go through what is we call AC circuits. So AC circuit meaning that you have a voltage source or the current source that is periodically, okay, periodic waveform. Okay, and okay. So AC, or in the full name is actually what we call alternating current, is the dominant form in electrical power. So the power that delivered to our house is actually in AC power. And but in late of this year, okay, there are battles between the people that are more pro to the DC and the community, okay, the engineers community that are more pro to AC. But eventually the AC won the battle, okay, because of what? Because of they said that actually if you compare DC and AC in terms of the losses, okay, so AC system has lower losses, so this is beneficial for what you call the transmission, because we know that the generator is actually installed at very far away from the community, okay, from the city, so we need the transmission line. So if we transmit the generator transmit using the DC power, so it will be higher losses. Okay, so that's why our system right now, all the power system is actually in AC system. Okay, so actually AC is actually a periodic waveform, meaning that it has is actually periodic, meaning that it's alternating. So we have a positive and negative values. Okay, so this is a type of DC and also AC waveform. So this is DC, and then this one we referred as an AC waveform. So we have sinusoidal, triangular, square wave, and there are others also signals. Okay, but in power system, we are using the sinusoidal waveform. Okay, so the sinusoidal waveform can be either down as a sine function or cosine function. So why sinusoidal? So actually, if compared to triangular or square wave, the sinusoidal is much more easier to be generated by the power plant. Okay, and it's also a signal that is dominant in communications. So that's why we are using the sinusoidal waveform as our AC power system. Okay, and sinusoidal is also easy to handle mathematically, and because it doesn't have any what you call linear part. Okay, so actually in a AC system, so there are two type of analysis that we can go, which is the first one is the on the transient response. So this is actually when there is a sudden change in the voltage or the current, so we want to see what is the characteristic of the circuit, how it respond to the step change. Okay, so this is what it calls transient response. Okay, and then the second one is the steady state response. This is much more to what we call a steady state, meaning that there is no disturbance, no step change, and so on. So actually, it's actually a constant, what we call a steady state. Okay, steady state. So so in this syllabus, we are focusing only on the steady state response. Okay, so the motivation. So how to determine VT and IT, okay? So how can we write down the equations of the voltage and the equation of the current? So because this is actually time dependent, okay? Okay, so the sinusoidal voltage, for example, can be represented using these equations. Okay, so V, I think this one should be V because we are the variable is omega t. So Vm sine omega t, and this waveform is actually like this, and as you can see, is actually periodically, is actually a periodic signals. Okay, so this one is pi and this one is 2 pi. So complete cycle is 2 pi, and in time this is called T, which is period. Okay. Okay, so instead of, as mentioned before, you can write down the sinusoidal voltage in sine function or cosine function. Okay, so it doesn't matter, but what is sine function is actually you write down this one as a v m sine omega t, and for the cosine function is actually v omega t vm cos omega t. Okay, and as shown before, this you can write down this one v, I think this one is a v omega t, this one v omega t. Okay, so you can, meaning that the axis is omega t. Okay, so full cycle is 2 pi. Okay, and you can also write down or sketch the waveform v with a variable of t, time. Okay, so your x-axis is time. Okay, so for full cycle, this one is equals to period. Okay, so this one is in second, while this one is actually in radian. Okay, so this one is actually in radian second. Oh, sorry, this one should be is actually the unit is actually in radian. Okay, so from here you can see that 2 pi is equals to time. So what is 2 pi? So in degree form is actually 360 degrees. So sometimes also you can find that the graph of the sinusoidal waveform here, instead of using pi, so it's using angle value. So pi, so we know that 2 pi is 360 degrees. So the half cycle here is equals to 180 degrees. Okay. So for this one, so this one is 90 degrees, which is pi over 2. So this one is actually is equals to 270 degrees. Okay. So the only difference is actually on the x-axis, okay? Because you can sketch the waveform either by using radian units. You can also use angle units, degrees units, or you can also use time units. Okay, so there are three different kind of sketch that you can use. Okay, so based on this waveform, so this waveform is actually using a sinusoidal function, sine function, okay, sine function. So for cos function, the waveform is like this. Okay. So this one is, so your full cycle is this one. Okay, so 360 degrees. So this one is 180 degrees. So at this one is 90 degrees and so on. Okay, but we're concentrating on the sinusoidal. So sorry, the sine function. So if this is a sine function, so you need to write down the expression of this waveform as follows. So V omega t is the voltage value at that particular point. For example, if omega t is equals to pi, okay, so it will give you the values. So once, for example, omega t is equal to pi, so you need to substitute omega t is equal to pi. So based on this waveform, if you sine pi, so it will give you 0 values, which is same with this waveform. Okay, so V omega t is actually the voltage value at that particular point. Okay, Vm is your maximum value. Okay, maximum values. Sine is your if your function of the sinusoidal, and omega t is actually what we call the angular frequency. Okay, which is in the unit is actually in radian per second. Okay, and so this is omega. Omega is actually your omega is actually in radian per second. What which is what defined is actually the angular frequency. Okay, or sometimes also the velocity of the frequency. And this phi here is the phase angle. Okay, and then it depends on the phase, whether it is leading or lagging. Okay, so it depends on the waveform. So this is actually the general expression. So this is the head of the equation and the V maximum and the function. So the sinusoidal repeat itself every t seconds. So t is called period, okay? And the frequency is actually the inverse of the p. So the unit is actually hertz, okay? So if you have more cycle completed in one cycle, so meaning that you will have higher values of frequency. Okay, so more generally, we need to account for relative timing of one wave versus another. So for example, we usually we compare. Okay, there will be many waveform. Okay, so usually when we want to compare, so what we do is, for example, this waveform. So how can we relate the different angle between this waveform? Okay, so this is the original waveform, which is V1 here, which is a sinusoidal waveform, which has an expression of Vm sine omega t. Okay, but the second waveform here, we have this waveform which is leading the V1 here by how many degrees, which is 5 degrees. And since this voltage is leading the V1, okay, so we put positive. Okay, positive, and the value of how how big the difference. So this is phi. Okay, the angle difference between V2 and also V1. Okay, so if you have your another, for example, V3, which is behind the V1, starting at this point, for example, and then with an angle of theta 2, phi 2, so your expression is Vm with this one is actually same magnitude. Okay, same magnitude. So you need to write down your V3 should be omega t here. Yeah, is equals to sine omega t minus theta. So minus meaning that it is lagging. So this is meaning that this is leading, and negative meaning that the waveform is actually lagging from V1. So we are usually use one waveform as our reference. Okay. Okay, so in electrical engineering, the phase angle is commonly given in degrees rather than radians. So I think in other engineering field, they prefer to use radians instead of degrees. But in electrical engineering, usually this phi here, the angle different, the phase angle is given in degree form. So the omega t is actually in radian, and the phi is in degrees. So if you want to sum up this, okay, what you need to do is to convert either one into radian or degree form. Okay. Okay, so but to compare this waveform, for example, two waveform, there are several requirements. Okay, before we can compare the waveform. The first one is that all the waveform must have the same frequency. What you mean by same frequency is actually on the angular velocity. So the frequency values is actually you can get from the angular frequency, okay, where omega is actually 2 pi f. Okay, the unit is radian per second. Okay, 2 pi f. So the frequency. So meaning that if you have, for example, the radian, sorry, the angular velocity, the angular frequency is 10, and your another waveform is also 10 radian per second. So meaning that it is obvious these two waveform has similar or same frequencies, because 2 pi is just a constant, right? So if you have similar, meaning that the frequency is similar, then you can compare. Okay, so this is the first requirement. The second requirement is that the amplitude for both frequency for both waveform must be positive or negative. Okay, what is mean by that? Meaning that if you have a voltage waveform, for example, you have V1 omega t. Okay, I think since okay, I want to draw like this. t is equals to 10 sine 10t, okay, and my V2 is 10 negative 20, for example, negative 20 sine 10t. So you cannot compare this, okay? So you need to convert, make sure that the value must be positive. So in next part, I will show you how we can actually convert this negative value into a positive value. Okay. So actually, what you need to do, the second requirement, you need to ensure that both are positive or both are negative. So if one is positive and the second one is negative, you cannot compare it. Okay. And the third one, the function of the waveform must be both either sine or cosine. For example, if your V2 is already positive, for example, positive 20, but the function is cos. Okay, the other, okay, the function is okay, both are positive, and the frequency is also same, but the function is not the same. One is actually sine and the other one is cos. So this is also cannot be used to compare. So you need to convert this cos into a sine function, okay, using trigonometry function. Okay, and then yeah, leading and lagging. So I have already discussed leading and lagging. So if your voltage is actually actually leading the V1, so this one you have a positive phi, okay. And if your voltage V3, for example, is actually behind the V1, so this one we call a lagging. So your V3 is actually lagging V1 by how many degrees? By this 2 degrees. So what happened when the voltage are the phase different, meaning that the angle, okay, the phi is equal to 0. So when this happen, meaning that the waveform are what we call in phase. This is shown here in this waveform. Okay, so if the phase difference is not 0, meaning that they are out of phase. Okay, so for example, a quick example here. So as you can see here, V1 and V2 are, obviously it is in phase, okay, because there are no phase difference between these two voltage waveform. What about V1 and V3? So V1 and V3, as you can see, is out of phase. And what about V2 and V3? So V2 and V3 is also out of phase. Okay. By how many degrees? This one is out of phase by 180 degrees. This is also 180 degrees. So if two sinusoidal are in phase, meaning that they reach their maximum and minimum at the same time. Okay, so as you can see, V1 and V2 are in phase, meaning that the maximum locations is actually at the same time. Okay. So as mentioned before, you can use trigonometric function to convert. For example, if you have this one cos, so you cannot compare, right? So you need to convert either one to be in sine or cos. So for example, you V2 I convert to cos. So what you need to do is to use the trigonometry here. So if I want to convert cos omega t into sine, so you need to have these ones to 20. So for example, this is my V2. 20 cos omega t. Okay, this is omega t. So after my conversion, I will have 20 sine omega t plus 90 degrees. Okay, so if you don't remember, so this is actually the trigonometric function that you need to remember. But if you don't remember, then I have a formula that you can use to do the conversion. For example, this one is sine, positive sine. This one is negative sine. Okay, omega t. This one is omega t. This one is positive cos omega t. This one is negative cos omega t. Okay, so for example, if I want my cos, okay, my equation is equal to cos omega t from sine. So what I need to do is actually, you see that the difference is positive 90 degrees. So clockwise positive 90 degrees. So this one is sine omega t plus 90 degrees. Okay. And if example, I want my negative sign from cos. So negative sign from cos. So still clockwise, so positive 90 degrees. So I should write my is equal to cos omega t plus 90 degrees, which is shown here. Okay. And if I want my negative cos from cos, so I should write down my negative cos omega t is equals to cos omega t, okay, 180 degrees. So plus 180 degrees. Or you can also use from here counterclockwise, so negative 180 degrees. So negative cos omega t also can be write down as a cos omega t minus 180 degrees, which is shown in this formula. Okay, so you can use this to you can familiarize this to help you on remembering this trigonometry function. Okay, so this is actually the conversion, so which is referring to the previous table. Okay, so right now the complex numbers. So inside the AC circuit, okay, we will majority of the equations will involve complex numbers. So what is complex numbers? Okay, so complex numbers actually in this case is actually we call as a Z, is represented in rectangular form as shown below here. So we have x and also plus jy, and in your calculator you usually enter your value as a yi, right? I imaginary, meaning that this one is the imaginary part. So this kind of representation is what we call rectangular form. Okay, and these complex numbers also can be write down as shown here. We have the values of the magnitude and with an angle phi. So this one, what we call is actually a polar form. Okay, so actually what is meant by complex numbers is that if you have a plane, so this is the real part and then this is the imaginary part. So this is your location of your x and this is the location of your y. So the intersection between real and imaginary part, okay, will give you the value. So this is what we call r, which is the magnitude, and the angle phi. Okay, so that is what you mean by rectangular form and also a polar form. So you can use your calculator to change from rectangular to polar or from polar to rectangular form. Okay, so these two forms can be what you call interchangeable, okay, interconverted to each other. And as you can see here, mentioned before, so you have x and we have the real part and imaginary part. So since it's actually okay, so for example, if you have a polar here, polar form with a value of r, you can get the value of x by using this formula. Okay, so x is actually r cos phi, and to get the value of y, so it's actually r sine phi. So actually z is equals to x plus jy, or in other form also this x z is also r cos phi plus j r sine pi. Okay, and the phi is actually usually used if you have y and x, is actually the inverse tangent of y over x. And this following shows the mathematical operations. I think this one is a very important one. Okay, I hope you can refresh back the addition and subtraction, multiplication, reciprocal, conjugate, and so on. Okay, so this is the addition. As you can see, you cannot add, simply add the complex numbers. So what you need to do is to add the real part only, and then you need to add also the imaginary part. Okay, real part with the real part and imaginary part with the imaginary part. The same case goes to the subtraction. Okay, for the multiplications, if you want to multiply the complex numbers, you can see that you need to multiply the magnitude values. Okay, but the angle you need to sum. Okay, for the divisions, z1 over z2, so you need to divide r1 over r2, the magnitude, and the angle is actually in must be subtracted. Okay, and then reciprocal, what you mean by reciprocal? For example, if you have z is equals to r phi, so reciprocal of z is 1 over z, so should be 1 over r phi. Okay, but this angle you can go up, so when you want to go phi, this one to go up, so it will become negative. Okay, so that is mean by this one. And for the square root, so if you want to square root the complex numbers, so the magnitude must be square root, while the angle must be divided by 2. And this one is the complex conjugate. So what you mean by conjugate is that if you have z is equals to x plus jy, if you conjugate, so the x z conjugate, meaning that the imaginary part will become inverse of the original polarity. Okay, so if you conjugate, meaning that the imaginary part will become inverse. Okay, if the origin is negative, then if you conjugate, it will become positive. Okay, so if you are in the complex numbers in the polar form, for example, r phi, if z conjugate, meaning that your value is still remain the same, but the angle is actually must be put in the inverse sign of the original one. So it become negative phi. So I think this one, you can simply do it. Okay, evaluate the following complex numbers. But I think by using calculator is quite easy today's, because during my time, we need to convert and then to write down first in the paper, and then enter back in the calculator. Okay, but right now the calculator has been upgraded. So it can be directly, it can be used directly to convert all the complex numbers, because before this, we need to convert. Okay, for example, if you have been given this rectangular form, we need polar form, so we need to write down first, and then we need to enter back the values in the calculator. Okay, but please be careful when entering these values, because it might be typing error here and there, so your answer could be wrong. Okay, so please be remind on that. Okay, I think that's all. For this one, I will do another what call videos. Okay, thank you very much.